Well, we did it. It's been 1 year since we got the first data from JWST, and it was amazing. We got all of these cool images of galaxies and exoplanet spectra, and then there's been a whole year of further results, and we've been reporting on tons and tons of them here on the channel. So to celebrate 1 year of JWST data, I thought I would organize a roundtable conversation with a couple of my astro friends. We've got Dr. Maggie Lieu, who is a research fellow of machine learning and cosmology at the University of Nottingham, and she is here to talk about the big picture stuff, the cosmology, the galaxies seen at the beginning of the universe. And also we've got Dr. Jessie Christiansen, who is a project scientist at the NASA Exoplanet Archive. She is the one who counts the planets who have been discovered so far, and of course was all over all of the exoplanetary data that we've seen, as well as some of the interesting solar system observations. So I have a roundtable conversation with Jessie and Maggie, and we just talk about the results of the last year. What are some of the interesting findings that we were excited about? What we see going into the future. So I hope you enjoy the conversation with Dr. Maggie Lieu and Dr. Jessie Christiansen. Enjoy. So we're recording this a year after the first science data from JWST went live and was available to the general public. Jessie, what's it been like living and working with JWST results over the course of this year?
Well, it's really interesting from the exoplanet point of view, because a lot of the early exoplanet science was the low-hanging fruit. They're like, let's look at the planets we know will have a great big booming signal and just see how beautiful they are. And that's what happened a year ago. They released these beautiful spectra of, for instance, WSP-39, and it's just gorgeous. So this reality coming true, everybody's been expecting these beautiful spectra for decades now, and now getting to see them, it's like, oh, yes, amazing. So the last year has been really fabulous in terms of sort of confirming things we already had a pretty good idea about. But I'm excited about what's going to come next, which is when we move to the stuff where we don't know the answer and we want to know the answer. JWST is the only thing that will tell us the answer.
So are you confirming known planets to kind of get a sense of how good the data is from JWST compared to other observations from other instruments? Is that sort of the primary focus at this point?
Yeah, so JWST is mostly looking at planets we already know. And, we have over 5,000, as I said. So some of them are going to be much better prospects for really doing a deep dive into their atmospheres, really investigating the structure, the composition, the temperature, the pressure of their atmospheres. Many of the planets are too far away and too faint for us to do this with. But there's hundreds that are close enough for us to really do a wonderful look with JWST. So JWST is mostly looking at known planets and planets where we know we'll see something cool, probably, if we look. There has been one planet discovered by JWST so far, where JWST looked at a system that already had a planet candidate in it, so something that the NASA test mission had seen as just a blip in the light curve, and they were like, ooh, if that's real, that's going to be a cool planet. So they went and looked at it with JWST, and they saw, and it's a cool planet. So there's one planet that's confirmed by JWST so far in test data. But mostly it's not a discovery mission in the sense of finding new planets. Mostly it's a characterization mission, taking the known planets and investigating them more closely.
And so Maggie, from the cosmology side, it feels like a very different story.
Yeah, well, JWST has been looking at the first stars and galaxies, and that's what it was designed to do, right? And it's just, yeah, it's been able to uncover them for us. And we're learning new things all the time. Loads of new candidates that people thought were the earliest ever galaxies, the first galaxies ever to be I don't know, the furthest away galaxies. And then it turns out that they're not, because these measurements are really hard to get right. And then other people, like Jessie said with the exoplanets, will come along and say, oh, we refute this. This isn't the furthest away galaxy. So, yeah.
And there have been a lot of things that JWST theoretically could get, perhaps really faint evidence of population 3 stars. And this was the kind of thing that you might see a decade into observations after all of the low-hanging fruit. But I'm seeing multiple papers every week now about people seeing hints and glimpses of some of the stuff that was way down the to-do list for this telescope. I mean, do you know what I'm talking about?
The thing is, everyone wants to be the first, don't they? They all want to be like, we want to have this first observation. So even if they're not like quite 100%, like let's just go for it. So it is exciting, and there will be like loads of follow-up and stuff to really figure this out. But it's hard to stay. It's still early days.
Yeah, I mean, I think whenever you push the boundaries of what we can do, and you end up at a new signal to noise level, right? Like now the things that were hard with Hubble, you see so clearly, and now there's smudges in the background of those, and you're like, oh, but what are those? So we're always at the bubble, right? Like scientists always want to just push past where we can. Yes, what we can do. It's like, oh, if only we could have done this.
Yeah, yeah. And I think with with both situations, you've got entirely new capability that's coming online, but it's fairly directed. And so you're not getting these sort of large surveys where lots and lots of things are turning up. So as you said, you're turning your telescope on known objects, increasing the fidelity and seeing what pops out of the image. For the exoplanetary stuff, I mean, the presentations are all charts. They're not, beautiful images of exoplanets, because it's a pixel, right? It's still a pixel. It was a pixel before. It's still a pixel. Every conceivable telescope we can ever make will give us a pixel. I'm amazed how excited people have gotten when they're being presented by what is statistical data. And they're grokking.
Yeah. So, I mean, part of that is, so I know you said, like, what were some of your favorite pictures? And I'm like, well, we have Spectra. They're not pretty. But
they are pretty.
Very beautiful graphs.
The real work and value and practice of these early JWST images has been capturing why this spectra is exciting, right? Like, we're not just showing you a spectra, we're highlighting this big bump and being like, this is the first time we've seen carbon dioxide for sure in another planet. That's what happens here. We breathe out carbon dioxide. We know what carbon dioxide is, like relating it to us and being like, this is water. We know what water is. Look, we see it on other planets. So really capturing why those spectra are important. And I actually think that people want to see the data, and I might be biased because I'm a scientist, but every article about exoplanets comes out with this like beautiful artist conception of this, imaginary world orbiting an imaginary star with features that may or may not be real. And every single time I'm like, yeah, but what did the spectra look like? Like, how good is it? Like, what are we basing this on? Yeah. So I'm all for the press team being like, here's the spectra. Like, let's respect the audience. Let's teach them. This is the spectra. This is what it shows us. That's why it's so cool. So yes, I don't have a lot of pretty pictures, but I have pretty spectra.
But whoever is designing those spectra is doing an amazing job, because they do look beautiful.
They are.
I was going to say they're not as interesting as just saying like what chemicals are actually there, because everyone gets excited about, potential life similar to our Earth, blah, blah, blah. And yeah, like what you said, they're really relatable.
Yeah, and I think that the public has had a diet of fake planets, right? A diet of imaginary planets with clouds. And then whenever you poke at it, it's like, do we know there's clouds? Well, no. We know that under this amount of water, under this temperature and pressure, there might be clouds. So that's why the artist put clouds. But I think actually, what I see in like social media when we're talking about these planet discoveries is people don't want us to overinterpret and present something that's not real. They want us to show you what we know. So I think JWST is actually going to do a great service of just being like, these spectra are so cool, they stand on their own. Look at it.
And how's that been for communicating this science for you, Maggie? I mean, they're pictures for sure. You could definitely see galaxies, but again, they're at the very limit. So they're just little teeny red blobs with meaning.
Well, some of them are, but others are like stunning, beautiful imagery. And actually you should, I guess you should think about astronomers as well. We generally don't look at any of this imagery data. We look at like black and white, very boring images. Someone will measure, I don't know, the shapes of galaxies for me, and I just get a number through. I work with catalog data as well, just like Jessie. It's just a table of numbers, not pretty images themselves. All these beautiful images that we're getting through with all the colors and vibrancy and all these, like, in the star, refraction patterns, that's all just for the general public. We don't see that. They're not even real colors, right? Because they're just different filters.
Yeah, I mean, there's some amazing image work that's being done. People like Judy Schmidt and people from the NASA Visualization Studio who are taking this raw data and just
I think it's so good
out,
that NASA.
Yeah,
I think NASA, like, making it open for anyone, like, to make these beautiful images, because we're scientists, right? We don't do this. We're not playing around with, like, Photoshop or whatever they use. It's great that the general public can actually get involved to make these beautiful images.
So if you had to choose, Jessie, what would be like the most significant story that you think has come out this year from JWST?
Ooh, okay.
I'm going to ask you your favorite picture, but as you said, right?
Yes,
but
I have a most significant story and a favorite story. The most significant story is probably that we looked at the first 2 planets in the TRAPPIST-1 system. So TRAPPIST-1 is this very, very cool red star. It's almost too cool to be a star. It's about as cool as you can be and still be a star. And it was discovered to have 7 rocky planets around it. And 3-ish of them, depending on how generous you are in the habitable zone of that star. So they're the right distance that if that planet had an atmosphere like Earth, water could be liquid on the surface. So there's 7 planets, and we've been really excited about these planets for a long time because we realized some time ago that these small cool stars make lots of rocky planets. But these small cool stars might not actually be good places for life. They're very active. They put out a lot of high energy radiation. And these planets might just not be able to retain atmospheres. It'd be like holding a hairdryer up to an ice cube, right? Like, can it actually stay, or is it just going to get blasted by this star? So for a long time, we've been really excited to look at these planets finally with JWST, which is the first time we've had the signals noise to do it, and ask the question, do they have atmospheres? So we looked at the first 2 of the 7 planets. So these are the 3 that are in the habitable zone. We looked at the first 2. Now, they are so close to their star, we didn't really think they'd have atmospheres. I think we kind of hoped, but we weren't sure. And it turns out they don't. So the results from JWST are the first 2 planets in this 7-planet system don't have atmospheres. So it's not super surprising, a little bit disappointing. But honestly, it's the next 3 that we really want to know, right? If you're in the habitable zone of an M dwarf like TRAPPIST-1, can you keep an atmosphere? Because we kind of think that's important for life. An atmosphere is needed to keep water liquid on the surface. If you don't have an atmosphere, water just evaporates into space because there's nothing holding it down. And we think water is necessary for life. So first 2 planets, no atmospheres. The next 3 are where I'm really excited. So that's probably the most significant story, but it's not my favorite because it would be better if they had atmospheres.
Well, those data were taken a year ago. So in theory, all of that is now getting dumped out onto the internet for any exoplanetary researchers to start digging through it and not wait for the scientists.
Yes, absolutely. And some of these were... Actually, I don't know if the TRAPPIST ones were early release science, which were specifically released immediately for people to look at. But now that the data are published, they're available in the MAST archive, the Mikulski Archive for Space Telescopes, MAST. That's where you go find them. All the data's there.
Yeah. So now the race is on, right? It's 1 year. We're 365 days tomorrow.
Yes.
So the race is on.
I'm excited.
Yeah. So what was the other one? Sorry, I interrupted you. What was the one that was your favorite?
So my favorite... and it's also a good image, is Fomalhaut. So JWST went and looked at Fomalhaut. And it's my favorite because Fomalhaut has this really storied history in exoplanets. So it's one of the few planets, or what we thought were planets, that we have the direct image of, where we were able to block out the light from the star that it's orbiting and see a planet around it. And there was this real race for a long time to see who could do this first. So we had seen in the infrared, like warm fuzzy blobs near stars that were mostly interpreted as brown dwarfs or substellar objects of some kind. But the race was on to actually find, like with optical imaging, just like visible light, planets near stars. And in November 2008, in a single issue of Science, 2 different planetary systems were published. So one is HR 8799, which has 4 planets going around it. And one was Fomalhaut. Now, people were excited about Fomalhaut because we already knew it has this huge debris ring. So kind of like, you know, how we have our asteroid belt in our solar system. So Fomalhaut has this huge debris ring. And the thought was there must be planets sculpting that ring. So they were like, let's go find the planets. And so they published this paper. They found a blob. It's in the optical. It's a planet. Everyone's real excited. And then they keep observing it for a few years. And they have an idea of what orbit this planet should be on if it is actually sculpting this disk that we see, this debris disk. And for a little while, it almost looks like it's maybe on that orbit, but not quite. But then the blob kept kind of getting bigger and fainter and bigger and fainter, which is not what planets do. So after a little while, they were like, wait, the new interpretation is that it's not a planet. It's some dust cloud that formed from the collision of 2 planetesimals. So 2 things crashed into each other, glowed for a while, and now that dust cloud is kind of expanding and cooling. And so what we're seeing is just like expanding, getting faint blob. So we already kind of had that thought before we saw JWST's data. So JWST went and looked at Fomalhaut, and we see this glorious ring. It's very Eye of Sauron, if you've ever seen the image. It's very imposing, and there's nothing there. We would see a planet if it was where it's supposed to be, and we see nothing. So this gas cloud over the last 15 years has just dissipated. What was cool was there was a different fuzzy blob, and for like a hot second, everyone was like, ooh, what's that fuzzy blob? And then immediately the internet sleuths were like, oh, it's a background galaxy, because Fomalhaut, the star in our galaxy, has moved over the last 15 years in front of a background galaxy, which now JWST, as we're talking about with Maggie, can see these faint smudges in the background now. So this faint smudge, we were like, ooh, no, it's a galaxy. So right now, Fomalhaut has no planets. Doesn't mean there aren't any, but we haven't seen any. But we still have the ring, you know, lidless, wreathed in flame, all-seeing, very Eye of Sauron-y.
Yeah, I saw that. I was talking about how time is allocated on JWST in one of my shows. And so I went, well, let's just go look at cycle 1 and just look what's coming up this week. And I squeed, like there's Fomalhaut. Oh, you know, this is it. I want to see this. And then
and that's the cool thing about the first year of JWST. We really looked at all of the like big classic planets that we've been loving for decades, and we got to finally look at them in this detail. So Fomalhaut was one of them, and there's no planet.
Maggie, your turn.
I am really surprised that Jessie didn't say about the detection of water on that exoplanet. That discovery.
Yeah, I mean,
and I thought you were going to talk about that one.
We've detected water on exoplanets so many times now. Like, that's old news. And
water vapor.
We found carbon dioxide for the first time. It was cool.
Yes. But JWST doing it, it's super exciting, I think. And it's always exciting when you say, oh, there's water.
Yes.
Planet.
Yes. That's something that speaks to people, that there's water.
I wish there was something more kind of that was like my area of science that I found super exciting, but there wasn't. Like all of them were like exoplanety stuff. I really like the solar system-y stuff, like Uranus having like the clouds that they spotted. Yeah, the rings were beautiful, but there was like clouds on there, and also the clouds on Titan. And I was just like, oh, they're all so cool, but nothing like, we've detected the furthest galaxy. I'm like,
this week.
Have you?
Right. Yeah. I mean, I think as you said earlier on that it was this race. And so for the first couple of weeks, it was just paper after paper saying we found the farthest galaxy.
Yeah, it was just a feeding frenzy. Galaxy.
Yeah, it really was.
And so many papers.
And then you got the second round, which was no, you didn't. No, you didn't. Yeah. And then finally there
like
was
a full measured week later, everyone was like, no.
Yeah, and then after that was we can probably agree that this is the farthest one, and it's far, but it's not as far as we'd hoped.
Right.
Yeah.
So even though most of the science is coming out,
I think JWST might find even further galaxies than we've found so far, but to have that straight away, like it's just unlikely, right?
So there wasn't like a result that came out from a cosmology perspective that resonated with you in a way that that made you feel like we're making some real progress here? Because, I mean, there are just these big, big questions about how the building blocks of the universe came together. What were the first structures? What came first, the supermassive black hole or the galaxy that it's within? How did the seeds of the cosmic web begin? Like, I think for me, it was that those results of the early cosmic web, seeing this one galaxy as an anchor with like 10 other smaller galaxies on their way into this linear structure that we see now everywhere across the universe. You're seeing just these first steps of what the universe would become. But nothing really just sort of...
Well, JWST is amazing for looking at the evolution of galaxies, right? Seeing the first objects and how they're different from things in our local universe. But it's a really small field of view. It's much bigger than Hubble, sure, but it's smaller than things that we're typically looking at when we're looking at the huge, large-scale structure of the cosmic web and how the universe evolves, like as a whole, like that, right? So
like when the Vera Rubin, Nancy Grace Roman, and Euclid all are working together, dumping out exabytes of data, that's when your eyes are really going to perk up.
Absolutely, yeah. JWST is perfect for studying individual objects up close, super high resolution, all the amazing spectra. But we need a huge sample of them all to figure out what's going on in the entire universe as a whole.
Do you have like a pet object you're hoping JWST will look at? Like a favorite galaxy?
A favorite galaxy? No, I don't think I do.
They're all good galaxies.
They're all good galaxies.
So I guess, I mean, I know you've talked about this quite a bit, but I want to sort of press this idea of like these impossible galaxies, this idea that the universe was more fully formed, more mature at earlier points than anyone had expected. Do you think that's true, or do you think that is a bad job on science communicators' part, like me, in representing what's really going on?
Well, we've learned a lot from JWST. We know that like the stars and galaxies, those first ones, they're a lot fainter than what we expected them to be. They have different elements and stuff. And that just does change like the models that we use to predict like what's going on. We don't know what happened at the start of the universe. Like everyone talks about the Big Bang, but did the Big Bang actually happen? There are theorists that are working on different models that are not the Big Bang, right? That's just a projection back. And so learning about these first stars and galaxies, seeing through that opaque early universe, we are learning huge amounts of information. And that will steer what our models tell us, steer us what model's correct, right?
But everything's still sort of, I guess, everything is fitting within some of the models. Like
they didn't break physics yet.
They didn't break, no. Physics are not broken.
Well, they thought they did, right? At first, there was one galaxy that was older than the age of the universe.
Yes. I remember.
Oh, wait. No, that was wrong.
Yes. Usually that's your first sign that you did something wrong.
Yeah. A star older than the universe. Maybe the stellar physics you're using is incorrect. So I'd like to talk about like what it's been like being scientists, seeing the data and sort of its impact on the scientific community, because, you know, we're dealing with this situation where the data, some of the data is just being released immediately while other of this data is being held for a year. This is done, you know, NASA doesn't tend to do this, but European missions will do this, like with Rosetta and stuff. Jessie, what do you think what is the sort of feeling from the exoplanet scientists about this?
Yeah, there's been a big sea change, I would say, in the last even 10 years about data access. So most NASA flight missions do have what we call is like a GO period, a guest observer period. So if you put in a proposal to Hubble, they'll hold the data for you for 12 months. And you can ask for less or try to justify more, but there's like a standard 12-month period. And the same was true with Spitzer, NASA's Spitzer mission that was turned off a few years ago. So NASA's flight missions, if you propose for data through some kind of guest observer call, typically they will keep the data private for you for a while, right? To give you time to have your students work on it and get publications out. It's the big survey missions like Kepler and TESS where there's so much data coming out any given month, right? Like, just make it all available because there's many, many groups in the community who are all doing different science on the same data. It's a survey instrument, just make it all available. So you can see, hopefully there's like slightly different models there. Now, there has been this question in the last few years, especially now that JWST is launched and is working, of how the community should approach those periods. Like, there's this sense that some groups, as soon as the proprietary period is up, they're in, they grab it. They're like sitting there waiting for their Hubble data for like 12 months because it's, they're interested in that science as well. And they're like waiting for the other team to do it, doesn't come out. As soon as the 12 months is up, they grab it and they publish it. And so some people have feelings about that, right? Because, you're trying to protect your students, you're trying to create an inclusive community where no one feels like they're being excluded. What's the best way to do that? And there's a few different questions to ask there. Like, how do you get the best science? Well, that's probably with careful work that's not rushed, but it's also with multiple groups looking at the data, right? Like, so you really want both of those things. So how does a proprietary period help or hurt that? Then there's also like building community. How do you build community? How do you make resources available for teams that are typically excluded, right? Like if you're not at an R1 research institution where your advisor is getting every proposal that they put in, if you're, in a flyover state somewhere at a small university, how do you get access to data? You can only get access to publicly available data. So the argument there that NASA would make is that all data should be publicly available so that everyone has equal access. So there's multiple facets to this problem. I'm probably going longer than you want me to, but there's multiple facets to this problem, and there's multiple ends that are served by different decisions. So NASA's in the process right now of evaluating this for missions like Hubble and JWST. Should there be proprietary period on these like guest observer targets? So it's still an open issue.
I think having proposals is good as well because the students get a lot out of proposal writing. You get to kind of reinforce yourself, like, why is this science important? Right. And then like the people designing these missions kind of learn from it as well. Yes, this is great for this. Mm-hmm. Our next like spacecraft or telescopes should be designed to go into more detail for this because we can't do it at the moment.
Mm-hmm.
Yeah. Whenever I bring this up with people and I hear their perspective, I'm able to devil's advocate the other position, and they'll be like, yeah, no, that's a really good point. Like, it's clearly complicated and there's a lot of moving parts, and I don't think we're going to, and I don't think we're going to find a really simple solution that works for everybody. I mean, I think the answer is survey data.
I think the solution at the moment is quite good, like having some sort of proprietary period, and then after that period is over, making it public, which is what a lot of telescopes have these days.
Or it pushes more and more to survey data. So you've got the Vera Rubins, which are just pumping out exabytes of data
that'll be all
real time,
publicly available very quickly.
Yeah. I'm planning to do a live stream of just watching the results pop out and then having a couple of scientists will just talk about what that could mean. Right. Oh, found a supernova. Right. Oh, let's find out where that is.
The live stream will be of their servers crashing as every astronomer. Yeah, exactly. Like when Gaia first released their data and everyone tried to download it at the same time and they were like, oh, nope, wait.
Well, because they're actually going to run filtering locally on the data so that you will at least be able to, it's going to go here, it's going to try and find the highlights. Here's the supernova, here's the asteroid, and it's going to, as it finds them, it's just going to.
Here's the thing that changed.
Yeah, here's the thing that changed. And then the underlying data, if you're going to look for stuff that maybe the computer hadn't thought of, it's all there. And that's going to be many people's whole careers will be found from that. But we're not talking about Vera Rubin. That is not this conversation. So, we're moving into...
Everyone would be going for the low-hanging fruit, right? Even with like JWST, if it was all like open, everyone would be going for those nice planets that Jessie already mentioned.
Right. Well, and then to bring this back to JWST, there was just a big Cycle 2 proposal that got selected, which is basically for every single targeted observation that happens, like when we go and look at TRAPPIST-1d, the next planet out, this science program is to look in the background of those images for galaxies, right? Faint galaxies. Because turns out everywhere you look, if you go faint enough, there's a galaxy, right? You're going to hit a galaxy. So there's this whole program in JWST to do this, to make these data available for people to look for the other things that could be there, the background galaxies.
And then like a little mask over top of the specific object that they were directed at?
Actually, I don't know how they're going to handle that.
Yeah, it's interesting. So you mentioned cycle 2. So we're now just about to enter or have entered cycle 2, which is the next round. Yeah. So, what are some, and I don't know if you know specific targets, but what are some answers or some questions that you would be interested in learning more about? I guess TRAPPIST-1. We all want to know about TRAPPIST-1. But Jessie, what are you looking forward to this year?
Yeah, so the obvious thing is the rest of the TRAPPIST planets. We really want to know how far out from one of these small cool stars you can be and hold an atmosphere. There are other M dwarfs that we're looking at in cycle 2 that have planets around them. So it's not just because, there might be something about TRAPPIST-1 that makes it different. Now we have the ability, now we're in cycle 2, it's like we can start branching out and looking at other things. So cycle 1 was a lot of the really big planets and then a lot of the rocky planets around M dwarfs. I'm really interested in this kind of big mystery that came out of exoplanets, especially with Kepler, which is that the most common kind of planet is a planet in between the size of Earth and Neptune. So we call them either sub-Neptunes or super-Earths, depending on where they are. And if you actually look at their distribution of size, it's not like a power law, like you don't just have more and more smaller planets, like most things in nature are a power law. What we see is this bimodal distribution. There's a big bump at around super-Earths, so like 1.5 times the size of Earth, and then a big bump at sub-Neptunes, so like 2 to 2.5 times the size of the Earth, and then a valley in between, like between 1.5 and 2 times the size of the Earth. Nature doesn't like to make planets. We don't know why. And we don't know what differentiates between the super-Earths and the sub-Neptunes. So in cycle 2, there's a bunch of these we've done all of the cool, hot, big stuff that looks great, and we're starting to answer these big questions about atmospheres of rocky planets. But there's this other thing, which is like, why do small planets look like this? Why do we have this bimodal distribution? So I'm excited to see the compositional differences between those two groups to start to see if we can say, this is when nature makes this size planet, and this is when nature makes this size planet, and this is why there's nothing in between.
And taking the spectra of the atmospheres will be key because you'll understand, are they rocky or did they have their atmospheres blown away?
Yes, and also if you can start to get ratios of the elements in the atmosphere, so like carbon to oxygen, that can tell you where the planet formed relative to the star. So a lot of these systems we see very close in planets that we don't see in our solar system. And we usually think they've migrated in, right? They formed further out and then migrated in over some period of time through some mechanism. And the different mechanisms actually predict different timescales and different C to O ratios. And that'll also help us work out like why is this bimodal distribution. So if we start to look at ratios of elements, we can say, okay, so these ones actually formed really far away and came in very quickly. So that probably happened while the protoplanetary disk was there, the disk of dust and gas that the planets formed out of. Or if it happened really slowly, then it had to have happened after the disk was gone and be due to something else, like interactions with another body, exchanging energy and then migrating in. So it's looking at the atmospheres and getting these ratios of elements, or even just the presence of elements, right? Like if you have water, then you formed far enough out in the solar system that there was water.
Is there a biosignature that we might be able to try and keep an eye on? I know the community hasn't even decided if they can think of one yet. But
so the simulations that were done before JWST launched was that if there was an Earth-sized planet in the habitable zone of a nearby solar-type star, so I think it was out to maybe 10 parsecs, that it would take every hour of JWST's 5-year mission to detect that signal, to detect the Earth and detect a signal in its atmosphere. So maybe in one of the extended missions, we can go to NASA and be like, hey guys, can we just spend 5 years looking at this star? Seems like other people, like Maggie, for instance, have different science they want to do with the telescope. It's not just a planet telescope, unfortunately. So we're not thinking that JWST will be able to help us with Earth-like planets around sun-like stars. But let's come back to rocky planets around M dwarfs. Now, the signatures of rocky planets around M dwarfs are actually much easier to find because the star itself is much smaller. So the relative signal of the planet to the star, if you put the same size planet around this star versus this star, it's much easier to see the planet around the small star. So we are hoping to really get a good look at these atmospheres of rocky planets in the habitable zones of M dwarfs and see what's there. Now, we don't have like a obvious biosignature that's just going to answer everything. Like, it's not just like, I saw water, there must be life. Because we know there's water in our solar system where there isn't life. So one of the things people are thinking about right now...
Do we know there's no life there?
That's a good point.
We should go check.
There could be, yes, we should go to Enceladus, for instance, and check to make sure there's no life. So far, there's no life elsewhere in the solar system. Get in the comments and tell me all about all of the life that you think is in the solar system. But we want to look for biosignatures in these rocky planets around M dwarfs. So it might not be a single molecule, but a combination of molecules that points at some disequilibrium chemistry that could point at life. So that's kind of where the work is right now. What's the combination of atoms and molecules at what temperature that can't be created by geology or volcanology or physics? You know, what has to be biology? What has to be life? We don't know yet, but we're thinking about it.
And Maggie, for you, what, as this next year rolls on, what are you going to be watching and are hoping to hear from JWST?
I think everyone in my field is excited about the galaxy evolution side. I'm excited about the lensing side because the high resolution of JWST is like incomparable. And we've already imaged like not JWST, but with Hubble, we've imaged the furthest star ever seen through gravitational lensing. And it's no doubt that JWST will be able to see many more of these systems, especially like even with the first galaxy cluster that JWST imaged, SMACS 0723. That was beautiful. And the mega galaxy cluster, Pandora's cluster, beautiful lensing effects. So seeing more of these objects, being able to use these objects as giant magnifying glasses to see even further into our universe is going to be super cool.
So the most powerful space telescope ever built is not enough. You want the additional lens on top of it that gives you another 10,000 times magnification.
Yeah, absolutely.
I'm telling you, scientists are never happy. Like, as soon as you show us the next horizon, we're like, but what's past that?
What's past that? Yeah. So, I mean, what are some of the kinds of things that could turn up in these gravitational lenses, do you think?
Well, seeing stars outside of our galaxy, being able to image these, that's already one thing, right? But even potentially from planets, like we get micro lensing measurements, right? So you can see exoplanets in that. So having gravitational lensing effects is just like, we can see anything. We can see like I bet if we see the furthest galaxies, it will be from one of these massive, massive galaxy clusters.
Right, right. And I mean, there are some pretty amazing things done with measuring the expansion rate of the universe. There's the potential for seeing even gravitational waves through gravitational lenses. I mean, I 100% agree with you that these gravitational lenses are just so useful and so powerful. Seeing supernova go off 4 different times in some distant galaxy because of the gravitational lens, and using that to measure, the mass of the lens, the speed of light.
Now I'm just like totally lost in the math of how you use gravitational lensing to detect gravitational waves.
Yeah, so you would detect the same gravitational wave multiple times. Do the waves
also get lensed?
Yeah, they do. So you would detect the same.
They also get lensed.
Yeah, so you would detect the same gravitational wave multiple times coming at you, because about 1% of objects are seen through gravitational lenses. And so in theory, once we get enough of that data, about 1%
ditch all the exoplanet stuff. That's the coolest thing we talked about.
Yeah. And so, but that has nothing to do with JWST. That has everything to do with LIGO and Kagra and Virgo and the Einstein telescope.
Yeah,
and
even
LISA.
with the supernova stuff, I don't think JWST would come back and observe the same supernova several times over 90 days, would it? So
That's a lot of time to
maybe
to
in
set
one
aside.
of the extended missions.
Yeah.
Yeah.
Maybe after the 5-year.
That's right. We'll take one of the extended missions to just look at a nearby Earth-like planet. And we'll take the next extended mission to just look at the gravitationally lensed cluster and see if we can see multiple things.
Yeah.
But I
agree. Let's shake on it. And we're good.
Well,
We've solved it.
That era, we just booked up all of the time. Yeah. But this era of being in
next 10 years of
multi-messenger
JWST is done.
astronomy. Yeah. Multi-messenger astronomy for me is the larger trend that makes me the most excited. That astronomers recently produced an image of the Milky Way in neutrinos using the IceCube telescope. That we are detecting both the electromagnetic radiation and the gravitational waves from two neutron stars colliding with one another. That you suddenly have these ways to look into these places that you could normally not see because they're obscured by stuff. And now suddenly gravitational waves, neutrinos don't care about stuff. And so and I would love to see, maybe, the times are really booked on JWST, but for it to be able to join the fray of the instruments that turn quickly when something really interesting happens is going to feel really valuable. And I think, back to the Vera Rubin, which we're not talking about today, definitely not. It's going to be turning up so many interesting things that they'd better set aside like half JWST time to just turn quickly and do follow-on observations of this mind-boggling thing that's never been seen before, because that's how often this stuff is going to happen. So it's a funny time, I think.
For your listeners who might not know how it works, so I mentioned geo proposals before, where you go to the telescope and say, hey, I would really love 6 hours to look at this target. And if you're really lucky, they give it to you. But then there's a different group of scientists who are like, I would like 6 hours whenever a supernova goes off to look at that supernova. And the time allocation committee is like, yeah, okay. So then you, with your precious 6 hours that you proposed and beat out 8 times as many people to get, halfway through, they're like, whoop, nope, can't keep looking at that because the supernova went off. And you're like, no! And it just happened to all of us at some point. And I love the supernova people, but also, oh my God, guys, stop doing it in the middle of a transit.
Right. That was it. We could have seen large amounts of ozone and oxygen and methane in the atmosphere of that planet.
Right.
And we missed
Maybe
it.
this was the transit where we found a biosignature, but now we're off looking at a supernova.
Yeah. Yeah.
Very inconvenient.
Maggie, if people want to follow your work, what is the best place to do that?
I'm on every social media, so you can follow me everywhere. YouTube, Twitter, Instagram.
And what is the
TikTok,
handle
everywhere.
to search for?
Space Mog, like the cat.
Like the cat. No, but people outside of Britain don't know that Mog means cat.
What?
We do.
I didn't know that.
Yeah,
I'm only
they
one
don't
step
know that Mog
removed
means
from
cat.
Britain.
We have this whole series of books about Mog, and it's a cat. And I've read them to my children for years. And they were 6 years old before my husband, who was an American, realized that Mog meant cat. And I'm like, that's the whole thing of the book. It's called Mog.
Does Mog mean
It's about
cat
a
the way
What?
boot means trunk? Or is it just like a
I mean, it's
nickname?
more slang than that, but it is just like a word for cat.
All right. All right.
Mog. Moggy.
Yeah.
All right.
So she's a space cat, which is funny because my Gmail address is AstroKitty.
Oh.
And she's Space
What
Mog. And I'm AstroKitty.
There you go.
Jesse,
It all
if you
comes
want to
together.
follow your work, what's the best place to do that?
Yes. Well, still probably Twitter, which I say with sadness because Twitter is very much going down the tube. I'm at Aussie Astronomer. I'm on Twitter. I'm on Instagram very vaguely. I'm on Blue Sky very vaguely. Still mostly Twitter. I'm hoping we can pull it out, but I don't know if we can. But yes, but please reach out. I'd love to answer questions.
Wonderful.
I think you should change to AstroKitty.
Well, I think I got AstroKitty because I was one of the beta invites to early Gmail, right? Before Gmail was open for everyone, I was one of the early beta invites. So I got to choose what I wanted. I didn't think I could choose AstroKitty on any social media these days. It would be gone.
Well, guys, thank you so much for taking the time to chat with me today. It's super fun. What a year it's
Thanks for
been.
having us.
And when you think about the fact that we could be looking at 10 years, 20 years, 25 years. I mean, it's just going to be better and better and better.
It just has fuel for like 10 years, right?
No, it's probably got fuel. I interviewed the
launch went so well that they revised
Yeah.
their fuel estimates upwards of 10 years to more like 15 to 20.
Or 25. Yeah. Yeah. So it could be around for a long time.
Destroyed by all the floating
That's a whole
rocks.
other conversation. Yeah. Yeah. I mean, they've actually turned the telescope around so that now the micrometeorites are not hitting.
Hit the back of it, not the front.
Yeah, they're hitting the back of it.
Well, that
That's
was
exactly
a super
it.
that was a huge discovery, right? Because they undercalculated. They didn't think there was that many micrometeorites up there until they actually sent it up there. That's actually my favorite story. That would be my favorite story.
They've completely changed the way they direct the telescope, so it's always now looking down orbit to be able to minimize the impacts, because now the impacts are not. It doesn't have its face into the wind anymore, and that's purely because of that
relative
impact.
velocity is decreased.
Yeah, 100%. All right, guys. Well, thank you again so much, and hopefully we'll look back in another year or two and see how things are going.
Yeah, thank you.
Thank you.
A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Joel Yancey, Antonio Lofilara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltonan, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.